So we're going to be talking about machine learning and deep learning. How many people here know more or less what machine learning refers to? Okay, and how many people here know more or less what deep learning refers to? Okay, I'm glad I started with a slide about what machine learning is then. Can we bring up my slides? And while we're waiting for those to come up, I will give you a word picture. So machine learning refers to anything where a computer is, we're getting a computer to figure out how to solve a problem, not by programming it line by line, piece of logic by piece of logic, but instead by giving it an example of the kind of outcome we want and letting it figure out how to solve the problem for us. So hence machine learning. It's not a new thing. It goes all the way back to 1954 when it was first used to program an IBM mainframe to play checkers better than the programmer that created it. Machine learning is also not new in medicine. This is quite a well-known example here from 2011, something called CPath, the computational pathologist. This was created by Andy Beck, Daphne Koller, and others at Stanford. And what they did, this is a really classic example of machine learning. They started with some pathology slides. And what they wanted to end up with was a probability of survival over time. So how did they get from here to there? The first thing that they had to do was they had to have a lot of domain experts sit down and come up with some hypotheses about what kinds of features in these slides might be related to the probability of survival. And so here are some example relationships of contiguous epithelial regions with underlying nuclear objects, blah, 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 relationships between epithelial and stroma objects, and so on and so forth. The domain experts came up with about 700 ideas for features of an image that might be predictive. Computer programmers then developed programs that basically calculated those features for each image. And then this big table was put into a machine learning algorithm. In this case, a simple algorithm called logistic regression that a lot of you would have come across in your academic career. That was then, the results of that were then looked at to build a 5-year survival predictive model. Interestingly, in this particular case of the computational pathologist, this predictive model turned out to be more accurate than the pathologists from Stanford that it was compared against. Furthermore, this model showed that the parts of the slide which actually did not contain cancerous cells was just as useful in predicting survival as the parts that did, which was really the opposite of what pathologists believed at the time. So this is a great example of machine learning used to build a predictive model and also create some new, really interesting clinical insights. Deep learning is a way of doing machine learning that's much easier and more accurate because you don't have to have the domain experts and the programmers sit down and create the features. The features are created automatically. This is an example, for instance, here's some photos of my team at Enlytic. When we run this through a deep learning algorithm, it automatically creates a hierarchy of features, edges, face parts, full faces, and so forth, which allows us to recognize the faces. These are, interestingly, these hierarchies of features are not programmed at all. Nobody said create some edge detectors, create a nose detector. Deep learning does this automatically using a deep neural network. This may look very familiar to you. It looks a lot like Spiro's earlier slide of the hierarchical temporal memory based on how the brain works. This was not intentionally created to attempt to replicate the brain, but it turns out that deep learning automatically creates features that very closely replicate how the brain seems to work. So this has been a very interesting insight from deep learning. So deep learning is a really exciting advance in machine learning. It allows us to do things that seemed impossible as little as 2 years ago. For example, these sentences were automatically created by deep learning algorithms that had never seen these photos before. So, man in black shirt is playing guitar is a novel sentence generated by a deep learning algorithm that had never seen a man in a black shirt playing a guitar before. So deep learning at this point really does understand images, it really does understand language. In fact, image recognition with deep learning today is more accurate than image recognition by humans. And this is in peer-reviewed literature that's really been shown in the last couple of months. If you want to learn more about deep learning, look up my name on TED.com. I have an 18-minute talk about both what it is and the implications of it. It's pretty exciting. We've been applying it to medicine, which is particularly exciting. When, for example, we tried applying deep learning to the National Lung Screening Trial data, we compared it to a panel of 4 human radiologists, and the false negative rate on looking at lung CT scans for lung nodule malignancy classification went down from 7% to 0%, and the false positive rate went down from 66% to 47%. So again, we're seeing better than radiologist level accuracy on early detection of lung cancer using deep learning. So it's a pretty exciting, so machine learning is something that goes back a long time and is very widely used. Deep learning, much more recent. But it is used, for example, if you have an Android phone, the speech recognition is using deep learning. Google Photos and Facebook both do face recognition with deep learning. So deep learning is increasingly getting used, although our company was the first one to use it in medicine, where it's a much more recent advance. So there's a quick bit of background introduction, and let's hear a bit more from our panel.
Okay. Hi, and thanks for having me here. My name is Wout, and we're the company which is called Deep6. We started actually working for the intelligence community, and we recently moved into healthcare. We started with something which is very sexily called epistemological machines. My marketing manager kills me if I even bring that up. But our aim is to actually use data and use machine learning, supervised and unsupervised deep learning, to find and create new knowledge based on disparate data sets. What we believe is that when we're talking about innovation at this panel and the whole conference, is that innovation or knowledge creation is something that is basically going on all the time, everywhere. It may be at very small incremental steps, it may not get measured, but a lot of it is, a lot of the questions around it is how do you diffuse that, how do you expose it, how do you connect that, and how do you see something that somebody working on in one part of the universe has great implications for somebody working on something else somewhere else. If you could just recombine that and do that at what we call machine speed and scale, can you actually unyield new knowledge or show new knowledge? What we're doing in this case, we started looking at EHR data, unstructured text data, and doctor's notes, and first doing some kind of a simple NLP to pull data from there and to yield what we call entities, salient features like symptoms, diagnostics, outcomes, tests, etc. And then look at the relationship between those entities and connect those relationships across a much larger data set. See, okay, if we have this cluster of entities here, how many other instances of similar clusters do we have? What type of relationships are there between those? And what can that really tell us about the prevalence and the correlation between these entities? We believe that by combining this at a massive scale, you can find what we call the tribal knowledge, the new innovations, the knowledge that's being created in EHRs that people are doing on a day-to-day basis as they're kind of perfecting their craft, nurses, doctors, therapists, etc. Pull that from that data and combine it with others to kind of see, okay, is there value to this tribal knowledge? Can we expose this? Can we correlate this? Can we test this? And can this gradually become formal knowledge? Can we do research on this? Can we kind of say, okay, well, yeah, this has value, and this can be done in double-blind A/B testing, etc. We can now actually write papers about this, make sure that this gets diffused throughout the community. So that's kind of in a nutshell what we aim to do.
Thanks, Walt. I'm very interested. You and I share a background in that we're both ex-McKinsey consultants who have kind of turned into data scientists later in our career. Could you give me a sense of whether you feel like the understanding of strategy and context is impacting your ability to be an effective data scientist today?
Absolutely. I picked up on that as well, actually. I think there's two things that I take away from McKinsey. One is indeed the hypothesis-driven thinking, right? Strategically, it's like, well, I think there's something there. Now let's find data to prove this. Let's try to see if we can do this at scale and quickly. The other thing, which kind of informs this whole connect and aggregate, is, as you know, McKinsey was really good at combining data and knowledge across all the engagements, curating this and sharing it back to the team. And that's kind of what we want to do right now, is taking massive amounts of data across many hospitals, physicians, etc., distilling the key knowledge from that and recombining that and pushing it back. So that's definitely McKinsey.
So then on the other hand, if you were going back to McKinsey today or to one of McKinsey's clients, what would you be telling them? Hey, now that I have all this background as a data-driven decision maker, what would you be saying? These are things that you should be doing differently. What are new insights that you've developed in this phase of your career?
To McKinsey consultants?
Or to folks, running the strategy and operations of a healthcare provider, or, anybody who's making decisions. I guess I felt like at McKinsey, there was a very heavy influence on expertise and experience, and, you interview experts and find out what they say, and nowadays I feel like most of my decisions are made by analyzing data. I feel like it's kind of a very different approach in some ways.
True. I mean, one of the things that McKinsey really did, right, there's a lot of human curation in their knowledge, in their expertise. It's a lot of looking at stuff, digesting it, regurgitating it, and then pushing it back, right? I think today, a lot of it is more data-driven, and with the technology that we're both working on, deep learning and other things, you can find patterns in the data much quicker, and you can have a more intuitive grasp of that.
I mean, that almost seems like exactly what we're talking about medicine as being where medicine should go. Your description of what McKinsey used to do sounds like a description of maybe almost what doctors do today, which is to pull in a lot of information and kind of digest it and regurgitate it. And a lot of this conference is about changing that into a kind of data-driven approach to medicine.
Absolutely. I think the key today is, right, the way that you consume knowledge is it takes a lot of time out of your day. You have to look for it. You have to know what you're looking for. You have to go through a lot of noise before you get to the signal. Then you have to kind of digest it. Then you have to apply it to your field. What we want to do by finding this correlation between data sets and what deep learning and machine learning can do basically is point you there. It's kind of precision recommendations. It's right, recommenders that say, well, this is something that will be interesting to you.
Right. Thanks so much. So Ken, here we go. Tell us about this.
All right, thank you very much. So my name is Ken Farrell. I'm a data scientist. I work for Dignity Health, which is a very large hospital system here in the Southwest. And when Anthony asked me to talk about big data and machine learning, I said, well, are those necessarily integrated? We do quite a bit of machine learning at Dignity Health and this is actually David's slide, I believe. But anyway, we do a lot of machine learning at Dignity Health with, I don't want to call it little data.
Is this the right slide for you? We'll find your slides.
Oh, that's definitely David's stuff right there.
Okay, let's find your slides.
Yeah. Anyway, so we do quite a bit of machine learning. No, mine's not quite that elegant.
Oh, okay, never mind.
I can speak to it without the slides. So we do a lot of machine learning without big data, and I think a lot of organizations may be somewhat intimidated to think that they're integrated, that there's somehow a link between your ability to do machine learning and your infrastructure. Do you have a big data infrastructure? Now, we do know, we've seen some of the speakers earlier talk about the Dr. Shang likes to call it the tsunami of big data. And as a data scientist, what I said we really need organizationally is a repository that can serve as a single source of truth for data that spans our enterprise, everything from our EHR system to our admission systems, to our costing systems, to our patient satisfaction scores. Just a myriad of data, our care management software that holds a lot of information about what our care managers are doing. And we can really answer a lot of questions. We can do a lot of data discovery if we have this single source of truth that can be put together at the organizational level. So my pitch as a data scientist was to tell organizations and to tell individual clinicians, if you have a question, have a place you can go to, an analytics institute, if you will, at your organization, where you can say, here's my question, here's what I think might be relevant to that question. Do we have that data? Has it been codified as official data? We're doing that at Dignity. I know there's a lot of systems that are doing that across the country. So once you do that, you can do what Russ Altman likes to call science tonight. So during our workshop, we had our workshop earlier on Wednesday, and I recognize some of you were at that workshop. In 20 minutes, I was able to take data that was already cleansed and conditioned and develop some very powerful models. And I was kind of taken back by the amount of surprise that the audience had that in 20 minutes we were able to do that. But that
And
was
what tool were you using to?
we're
to
using
build this?
R. So
Using
R is a statistical programming language. It's great for students because it's free. It's great for anybody because it's free. You can actually do some like ad hoc stuff in R without having
I do the same thing at Singularity University for my executive program. I show them a 20-minute R model, and people are
Right.
always, a free piece of open source software, which is so powerful.
And it only works, you can only do that 20-minute exercise, as you know, if the data is ready. So people say 80% of data science is getting data ready, and in healthcare, it's probably more like 95% of the time is spent getting the data ready. So if you can build that, you can actually create a framework for your entire enterprise to answer questions and start to get ready for the tsunami of big data, because big data, if we have the Wi-Fi diaper, for instance, that we saw yesterday, or some of the more the wearables and insertables, you're still going to have to connect that to patient demographic data. What's their ER visit history been like? What diagnosis have they had? What medications are they on? Before you can really start to do some of the deep learning and some of the machine learning that could really advance. and innovate.
Interestingly, though, something I've found recently is, because I spent 20 years doing more traditional machine learning and switched to deep learning more recently, I found that with deep learning, the data cleaning seems to be a lot less important, because deep learning is kind of very adept at handling noise and unstructured data and stuff like that. So I hope that maybe less of our time will be spent on the data cleaning in the future.
And I agree with that, and I work directly for the CMO at my office, and he says, just get a bigger N, get more data, which would require more deep learning methods, and then some of that noise will go away. But healthcare data is specifically noisy, and you really have to do I believe, a lot of pre-processing. A lot of the signal we're trying to gather out of this data is very light. There's not real strong signals in some of the questions we're looking for. So the better you can get your data, and if it's already, you don't want to redo that every time you have a question. That's just exhausting, and you can't get much done. So
And can I ask you the opposite question to the one I asked Walt, which is you have a background in computational mathematics and in informatics. Do you find that deep technical knowledge is something that's helping you to do your job day to day now that you're doing a better job of that at Dignity?
I believe so. I mean, we actually work with quite a bit of, we actually work with SAS, who's another one of our vendors that helps us do our analytics. And they have a whole team of people that will help us do some of the machine learning parts of it. But they don't have the deep mathematical understanding on, say, why a support vector machine, how that works, or why logistic regression might be better for this particular type of problem. And when you get that deep understanding of why these techniques work, not only does it allow you to maybe kind of triage which techniques you might want to path down, but also what kind of questions you can go after.
And if you're using R, then by definition, I guess you're coding as well. So that kind of mathematics plus code is kind of the basic literacy almost for data scientists today.
Yeah, in my experience, basically, I spent 20 years as a coder writing lots of C++ programs
me too.
and database programs, all kinds of different languages. So that naturally kind of translated into machine learning.
Great. Thanks so much. Okay, so hopefully we've actually got the correct slides now.
Go ahead and go to the next one. There.
Next one.
Perfect. Okay, I'm going to talk a little bit about the trend towards openness with data itself and its implications for machine learning, and how my name is David Odge, by the way. I'm a student at Stanford University. I got involved with big data during a 6-year stint in the intelligence community. We used a lot of linking attributes of various events to come up with a more full picture of what kind of is going on. So my goal is to apply those same methods to understand a knowledge graph for EHR systems, as well as linked open data, which can be found all over the internet. It describes everything from drugs to genomics. It's very, very robust what you can find out just open source data on the net. So first off, I want to talk a little bit about opening up handwritten forms of data to the digital form. Clearly, everything's moving to the electronic health records in the clinical space, and that's clearly part of this data tsunami that's on its way. But how do you unlock that further and bring that into a more more of a knowledge base as opposed to just a database, and be able to use that knowledge for machine learning purposes. So secondly, we can use linked data or RDF format graph databases to seamlessly integrate data objects that are similar, but maybe have two different views on them. Maybe it could be a drug compound that has a metabolic effect, but it also has, you know, certain stereochemistry or something. We can get all those data elements as attributes of that particular drug, let's say, and then link it to a patient's record. And this is all data that can be slowly accumulated as more information becomes available, and it can be integrated seamlessly.
So the graph database you mentioned, I'm not sure how many people would be familiar with that concept. Can you tell us a bit about what a graph database is and why that's important?
Absolutely. So if you think about some of the more searchable programs on the internet, let's say IMDb, where you can look at maybe a genre of a movie, find a bunch of movies of that genre, find all the actors in a particular movie, and then link out to what other movies they were in. This is the back end of IMDb is just a large graph database. It's kind of like an internet for objects of data. So it connects, let's say, an actor object to all the movies that actor has been in, and then the producers of those movies that produce that particular film.
And you mentioned you came from an intelligence background. I guess Palantir is perhaps the most well-known graph database in intelligence. Is that something that you were familiar with?
I have worked with Palantir, yes.
Yeah, so that's something that those who haven't seen it, you know, can kind of link from an IP address to a list of known people that use that IP address, to a list of their terrorist connections, to a list of their phone numbers and so forth. And I guess the idea of bringing that concept into health, I mean, could you give us a kind of an example of a use case of how that might look or how it would work?
Absolutely. So let's say, for instance, we have EHR data. John Doe gets a prescription for a particular drug. That drug, and that's all that's in the medical record. All you have is the name and, let's say, a time and the drug that's been prescribed. Well, we can now examine through using linked data in a fully automated process what metabolic effects that might be having, that drug might be having on that patient at a given time. So you're able to pull in this additional outside knowledge really very, very seamlessly, because you recognize that the data object that is a prescription or a drug is the same data object that causes a certain physiological change for the patient.
Thanks so much. Sorry?
We have it ourselves.
Oh, I was told to own the clicker, but you can take it away.
Whenever you're ready.
I'm going to get in trouble. I was told not to give away the clicker, and I gave away the clicker. It's the big green button. Yeah.
Can I start?
Please.
Hi, I'm Suresh. Thanks for the opportunity. As pediatricians, how do we generally take care of inpatients? We take a quick look at the patient, we talk to the parent, then we look at the monitor, heart rate, respiratory rate, blood pressure, pulse ox, etc. Then we look at the EMR for labs, CBC, electrolytes, eyes and nose, and then decide, is the patient getting better or getting worse, or is it status quo? So basically, I'm looking at 5, maybe 10 pieces of patient-specific data and making some serious decisions. Now imagine if I was able to look at 25 to 30 such specific variables and then make an informed decision. And what if I can do this for every patient of mine every single minute? And what if that assessment can also include nursing notes, which are almost always textual and unstructured? My mind cannot do that, and I doubt if any human mind can, but a machine can. The Rothman Index does that. At Children's Hospital of Pittsburgh, we worked with Michael Rothman and his team and co-developed the pediatric Rothman Index, which takes into account the age-based differences in vital signs and some changes in lab parameters in kids. Why is it so valuable? The PRI is a number from 0 to 100. Lower the number, sicker the patient. It incorporates physiologic measures, clinical assessments, and lab results into a composite index. And as we all know, nursing data is particularly sensitive to patient deterioration. When combined with key vitals and lab data, the PRI can flag patient deterioration much earlier, enabling us to provide better and timely care. So why is the PRI useful? It's universal across all pediatric disease categories. It's simple. If you have a score of 60 right now and 40 X hours later, that means you're getting sicker. It's real time, it's automated, uses existing EMR data, and it's integrated into our Cerner EMR. In our 4-month pilot, which was from April to July of last year, which was in silent mode, we had 110 alerts from 60 patients in the acute care units, and 16 of them eventually went to the ICU. Keep in mind, this was in silent mode, so it was retrospective. We now have prospective data. So about 25% of these alerts, we call them condition E, as an electronic and EMR initiated, they went to the ICU. The median lead time between those two arrows was 8 hours and 50 minutes. 8 hours is a lot of time for the pediatric hospitalist and the PICU to change care decisions. The expectation that we have now is the rapid response team responds to these alerts in 60 minutes. Every doctor in the hospital, every resident, every attending physician, every nurse has access to this, and it's in our Cerner EMR menu up front and center. The alerts are also transmitted to predefined phones so that the nurses don't have to be at the bedside all the time. Efficiently managing ICU beds and utilization is critical to a hospital's financial health, not just clinical health. And at CHP, we have done the math and figured out that a 1-hour drop in the length of stay for all our non-ICU patients yields us a savings of $1 million annually with very little added costs. We're also working on an NICU and a CICU index given the uniqueness of these patients. This evolved from the adult Rothman index. It's not specific enough for some set of pediatric patients who come out of the OR or transplant patients, et cetera. So we're working with them to refine that. We're also working on an international index. Every day we do rounds via telemedicine on a pediatric ICU in Bucaramanga, Colombia, where again, it's a unique patient set and they need a different index. So
And Suresh,
Yeah.
was this built using machine learning, or was this built using a more traditional kind of heuristic approach?
Machine learning, but definitely not deep learning. And with my limited technical background, I would probably say basic machine learning. It's a learning system. We validated this with our own patient data for about 2 years before implementing it. It's patented, published. And so the answer to the question is machine learning, yes, deep learning, no.
And what were the hardest parts of building this and rolling it out? Was it getting the data together? Was it integrating it into the EHR? Was it doing the validation? What was the most challenging bit?
Right, a little bit of all of the above. Once our intensivists got on board, when they looked at the pilot data and the validated data, and the 8-hour time frame, which is massive for the hospitals in the ICU. If you get that amount of lead time, I'm willing to have a lower area under the curve, a lower specificity, positive predictive value. Even if we can get 2 hours, that's a lot of time to provide better care.
Great, thanks so much. So you better give May the clicker.
Okay. So I'm going to talk about pediatric big data for intelligent health. I borrowed this word from Anthony and changed from precision health to intelligent health. So the first 2 P words are the enabling key component. One is the people. I think this morning Peter mentioned about the translation. Part of the translation required a close interaction between the clinical team and the machine learning team. So as a result of it, I'm actually listing on the bottom of the slides. On the left side, it's actually Georgia Tech. It's actually one of the top engineering schools in the US. We have multiple multidisciplinary team from Institute of People and Technology, Institute of Bioengineering, Bioscience, and as well as my department. I'm actually proud to mention that my department is the first department in the entire US that's jointly formed by a public university, Georgia Tech, and a private university, Emory University. And our department is right now ranked number 2 after Hopkins. And we are proud to be the first to start pediatric engineering and healthcare and informatics as one of our core competence for our academic department. And then on the left side is actually our chore team. And so in the middle, we see like Sherry Frugier and Kevin Mayer. I hope they're in the audience. They are very uniquely positioned. They actually have offices on both on Georgia Tech and the Children's Healthcare Atlanta. They're actually also being like supported by both the organization. And then on the right side, we have some key players in enabling it, including the leadership teams. For example, Mike Thomas, the VP for Business Intelligence, and then the chief for various departments from cardiac ICU. Kevin is the director. Tom Burns, who is the neuropsychology. Bill Milley, who is the chief of cardiology. And Shahida Bahig, who is the pathology chief, as well as Clark Brown, as well as them compare. Those people are the one who really enable the entire thing. I'm going to talk about this. So actually, I think early on, Jeremy mentioned about because of deep learning, probably data cleaning is no longer that critical. I actually disagree. Key thing is there are 200 to 400 patients die in US due to the medical errors caused by various issues. So deep learning is only be able to take care of some of the noises that's actually correctable. We still need a machine learning to differentiate the fundamental, the quality issue in the data, because some of the data are simply not correctable. So that's the part of the frontier in our community right now, is to use machine learning to differentiate those are correctable errors. For example, in the EMR, we have at least 25% to 30% missing data, and plus a lot of data with noises. So we have to differentiate those who are correctable and not correctable. On top of that, we need to be able to develop different strategy to handle that. Second frontier in the big data analytics right now is the data integration, which is actually already repeatedly discussed today. I want to quickly point out that one of the things is to bring the genomic with the imaging to do a better diagnosis. But more importantly, I think no one has mentioned yet, except Atu mentioned this morning, do we want to capture every single byte of data? In fact, if we're talking about precision medicine, if we cannot bring the genomic into the EMR, it makes useless to the real physicians. So that's why the integration of EMR with genomic is a very critical part of our integration here. The third one is, I think Shapiro mentioned this morning about knowledge. We keep talking about population-based study. Population can only provide you the knowledge. You do correlation, you find different patterns and groups. But fundamentally, at each individual of us, we care about the individual treatment. That personalized decision-making, why we need physicians instead of Dr. Watson, a machine, largely because of this inference capability. So that's another frontier in big data analytics. The last one is also very critical. This morning, we talked about cognitive computing. Natural language processing was mentioned. However, there's another key important part of the cognitive computing, in fact, is the self-adaptive learning. When we actually need to do real critical real-time decision-making, we want to utilize the population-based knowledge. But fundamentally, when we add individual cases, when every patient comes in the clinic, we want to be able to do adaptive learning. So these four are the state-of-the-art frontier in big data analytics. Thank you.
Thanks, Mei. And so one thing that particularly resonated with me was talking about combining EHR with genomics. The work that we do at Analytic has mainly been focused on medical imaging, and as I'm sure most people here are aware, the PACS systems where the medical images live are never integrated with the EHR, and as a result, at least not deeply integrated, so it's very, very hard to do true medical imaging analytics because the results cannot be attached to the imaging. It seems like from what you're saying that we may be entering into a similar problem with genomics unless people are careful to make sure that the same problem doesn't happen again.
So the question?
So would you agree with that? I mean, what is the state of the integration of EHR and genomics? Is there something where people are doing a good job of it, or is there something where people need to be thinking more about combining EHR and genomics to ensure that we can actually do the analytics?
In fact, right now, it's actually only the starting time. In the community right now, there are two different opinions. One opinion is we treat the genomic as a lab test. Come to the final conclusion, get some text into the EMR, so physicians just care about the final conclusion. However, the challenge is there are a lot of things we don't understand our genome. So like 3.2 billion base pair, there's so many things we don't understand it. So that's why along the way, when someone mentioned early on, while you're trying to do validation, understand science already changed, technology also changed. So how do you deal with this? As a result of it, the second opinion is actually keep the raw data, but do a layered information retrieval, interactive retrieval on real time for the physicians who care about what they want to know. So if we try to do that, the current EMR system cannot accommodate that at all.
Right.
As a result of it, using some visualization plus the metadata annotation, and plus keeping the retrieval of the base pair information on raw is becoming a top priority on how to
Yeah,
design
the EHRs just don't seem to be set up to store these larger data items. So, so in imaging, you end up with a whole different database, the PACS, that contains the medical images, and there's only kind of an ID link or something. And the same seems to be true for genomics. It'll be a whole separate database that contains the raw base pair data. And all the AHR will have some kind of summary. And unfortunately, that won't be good enough for machine learning, because for machine learning, we actually need to be able to bring the raw imaging data and the raw genomic data. In fact, as I'm sure you know, there's a area of research called radiomics, which is where it's looking at actually combining radiology data and genomic data together. And Dana-Farber, Hugo Ertz, is the guy who's been working on this. They've been finding extremely powerful machine learning, effective machine learning algorithms for prognosis in radiomics, combining the two together. But if we continue to have these silos, even within a single institution, there's genomics, there's radiology, there's pathology, there's EHR, then machine learning can never get started, which seems like a big issue. Yep. In the graph databases, is this, I mean, how do you create a graph database when the data in the first place is so dispersed?
Well, okay. Actually, that's really the power of the graph database, is taking a variety of data and integrating it seamlessly with the same data elements. So you take your patient IDs or whatnot, and you can connect all the metadata elements directly to that.
Well, I mean, that's true when it's there, but I mean, how do you populate it in the first place? If you came to, CHOC and said, hey, I'm going to set up this graph database, and they said, okay, well, here's our 4 PACS systems, and here's our, 3 different EHRs, and so forth. Like, how do you get through that?
Well, it's really more about making very clear which identifiers you're using, identifying, making sure that the patient is identified the same way in each one of the systems. It's very, very seamless after that, because really you're just setting up an association between that data element, whatever it is, in one EHR system to another data element in another EHR system. So it's really just drawing associations once you have the identifiers correct.
I guess the key thing is to just do it once. I mean, I think back to when I started building data warehouses 20 plus years ago in banking. At that point, every bank knew that step one was bring all of the company's data together in one place. And it's kind of amazing that in medicine, it's very rare to find a hospital that actually has all the data together in one place. It's still in separate places. It's just like, 20 years behind where other industries have been, which is quite extraordinary. But it seems like finally it's starting to change. Finally, some folks are starting to say, let's get all our medical data in one place so that we can then apply machine learning and cognitive computing and artificial intelligence. That seems to be like the key first step. And I know we were talking at lunch at UCSF. This is what they're doing, is getting all the UC hospitals, all the data together in one place. This is very exciting. And pediatrics seems particularly important, because pediatrics, childhood diseases are so difficult. You know, there's so they look so different, and you know, so it's great that the work that particularly like Anthony's been driving to bring many hospitals together. So hopefully one day we'll have a single data store for that. Are you guys aware of any other kind of interesting, successful work going on to actually create these effective medical data sources we can then apply machine learning to?
You know, we have the CHA, which is the Children's Hospital Association, has a database called PHIS, Pediatric Health Information Systems, which pools multivariate data from 80 or 120, I forgot, children's hospitals. So that's a good thing. But going back to your earlier comment, the reason for disparate silos in hospitals is, and as CIOs we deal with this every day, is the decision to go whether best of breed versus an integrated system. You know, if you have a great, you know, radiology suite, we buy that because it serves the needs of radiologists and patients, realizing that it does not do B, C, and D well. And the same cycle is repeated with the pathology software, with the financial software.
Yeah, I mean, that should not necessarily be a problem. You know, generally the data warehouse, at least in other industries I've been in, is not the operational system. It's a system that, you know, you've got your best of breed cardiology packs, you know, and then you've got your best of breed EHR for pediatrics, whatever, and each of those systems gets sucked into, you know, a data warehouse, which is or an operational data store, or even something like Hadoop, you know, nowadays, which maybe is even less structured.
Right. I mean, hospitals are going through that, and there are some, you know, use scenarios for Hadoop in hospitals, but early days.
Ken, what about at Dignity? You know, how did, you know, you're building early clinical risk detection stuff there. What are the data sources you're drawing from, and how hard has that been to pull together at Dignity?
Yeah, actually, we do have a Hadoop-based system that we pull from, and it does just what you say. It retrieves raw data from data sources. It doesn't do a lot of transformation on the data, which is contrary to the old data warehouse methodology.
Exactly, yeah.
Transform on the way in, and
Exactly,
everything's nice and homogeneous. So we have...
Perhaps makes it easier to handle the kind of changing dynamic needs of the rest of the business.
You transform it on the way out, but typically that means you have to, when you bring a use case to the data warehouse, you have to invest time to get that transform logic built up to get the data out. So it makes it a little more difficult to get things quickly turned around, but it can deal with large amounts of data and not a lot of rules on the front end. But what we have a problem with, so we have acute, we have ambulatory, we have PCP data, and what we need to be able to do is link those patient records across those systems seamlessly, which is not as easy as it sounds. We're always buying hospitals, we're always changing EHRs out. So it's a never-ending battle of trying to kind of make that data homogeneous, and that's been a challenge.
Do you use a data mart approach? So you've got the Hadoop, you know, cluster there with the kind of unstructured, pretty raw data. As you said, you have to interpret it on the way out. You don't want everybody to have to interpret it separately. So do you use something like data marts to kind of structure that once and then have that used for particular sets of analysis?
Yeah, well, right now what we have is kind of data marts that support different parts of the business. So if we're doing some clinical studies, we'll have a data mart that will pull the clinical data and put it together in a little area.
And that gets pulled from Hadoop.
That's pulled from Hadoop.
And then stored in some kind of like SQL system.
Stored in SQL, or even sometimes given to me just in a raw form of very large text files that I can import into my analytical tool of choice. But we really do need that discovery area where we can bring everything in once and then start doing some of those discoveries. Right now we have to go to them with the use case and say, here's the data we need out of Hadoop. Please help us get it out of Hadoop.
Yeah, it's such a great model when that exists. And, you know, thanks to Hadoop, I think it's made life a lot easier. Well, thanks so much to all of you. I really appreciate your time.
Thank you.